Welcome. Today, we are deconstructing the bedrock of computer science, linear data organization. We will not just look at arrays and lists as abstract concepts, but analyze how they physically interact with modern hardware architectures, caches, and memory managers. We must first distinguish between the logical and the physical. Logically, a sequence is just element A followed by B. But physically, inside the RAM, the story is different. Arrays unify these views through contiguity, while linked lists decouple them, scattering logical neighbors across physical memory space. The array's superpower is random access. It relies on arithmetic, not iteration. To find the location of the kth element, the CPU calculates address of k equals base plus k times size. While this address computation is mathematically constant regardless of size, physically accessing a massive array of 10 billion items may still trigger cache misses or page faults. However, arrays are rigid. When a dynamic array like a vector needs to grow, it cannot just expand in place. It triggers a heavy three-step protocol, allocating a massive new block, copying every single byte of data to the new location, and finally destroying the old block. This causes memory usage to spike and saturates the bus. There is a hidden advantage to arrays: vectorization. Because data is aligned and contiguous, modern CPUs can grab chunks of 4 or 8 numbers at once and process them in a single cycle using SIMD instructions. Linked lists, being scattered, completely break this capability. Now, let's look at the linked list. Its atomic unit is the node. Unlike an array element, which is raw data, a node carries heavy metadata. For a simple integer, you might pay a tax of 16 bytes of pointers just to store 4 bytes of data. This drastically reduces information density in the cache. We often hear that linked lists offer constant time, or big O of 1, insertion. This is a half-truth. The mechanical act of swapping pointers is indeed instant. However, finding the correct location to insert usually requires traversing the list, which is a slow, linear operation that negates the benefit. Let us shift our focus from software theory to hardware reality. This is where the theoretical advantages of linked lists often collapse. Modern computing is defined by the memory wall. The CPU is incredibly fast, but it spends most of its time waiting for data. Accessing the L1 cache takes 4 cycles. Accessing main RAM takes 300. Every time you miss the cache, your CPU stalls for an eternity. This leads to the pointer chasing problem. With an array, the hardware prefetcher predicts what you need and streams it. With a linked list, the CPU doesn't know where the next node is until it finishes reading the current one. This serial dependency chain creates a stop-and-go traffic jam in the pipeline. To fight these limitations, engineers have developed advanced variants. We have doubly linked lists for bidirectional travel. XOR lists use bitwise magic to compress 2 pointers into one field. Unrolled lists place small arrays inside each node to improve cache locality. And intrusive lists embed the pointers directly into the data objects themselves. In C++, vectors are truly contiguous blocks of data. In Java, an array list is actually an array of references to objects, adding a layer of indirection. And in Python, the standard list is a misnomer. It is technically a dynamic array of pointers, not a linked list. In conclusion, the array is typically king due to cache locality and prefetching. However, linked lists remain vital for scenarios requiring structural stability, such as intrusive kernel chains or specific lock-free queues, even though arrays are also capable of lock-free concurrency via ring buffers.